Hello students, let's talk about how we do some of these force problems. The first thing that we want to do for all of these problems every time is we want to draw a free body diagram. Right? We've practiced doing those before, and this will be the foundation for how we do all of these problems. The next thing that we want to do once we have our free body diagram is we want to sum up the forces on both the x and the y axis. And we practice doing that as well. Now, once we have those forces summed up on both axes, we want to set them equal to 0 if it's a first law condition. In other words, if we're at rest or if we're moving at a constant velocity. If we're not doing one of those two things, if we're moving at some acceleration, then that's a condition for Newton's second law, and we want to set that summation equal to ma. Okay, so those are the two options that you have. Set it to 0 or set it to ma. And then depending on how the problem goes, you will need to use a friction equation, most likely, either for static or kinetic friction. So after we do this step of summing up the forces and we use the friction equation, each problem will be a little bit unique, but this will be the foundation for how we do these problems. So if we take a look at a couple of examples, the first one that we'll do is we've got a chair that's sliding across the floor. The floor is horizontal, it's moving at a constant velocity, and there's a force of 127 newtons that's applied to keep it moving at that constant velocity. We want to find the coefficient of kinetic friction between the chair and the floor. So this is the first problem that we're going to do. The second problem that we're going to do is we have a child in a sled being pulled across snow with 140 newtons of force, and this time the angle is directed at 35 degrees to the ground. Right? Imagine that your arm is angled backwards towards the sled as you're pulling this child across the snow. So the child and the sled have a combined mass of 35 kilograms, and they're accelerating at 1.25 meters per second squared. And again, what we want to do for number 2 is we want to find that coefficient of kinetic friction between the sled and the snow. So these are the first two problems that we're going to do. Once we do these, we can move on to a little bit more advanced problems that involve tipping our axis when we have some sort of a slope or a ramp type of problem. Okay, so let's get started on these two. Okay, let's do our first force problem. So the first thing we want to do for all of them is we want to draw our free body diagram. So I'm going to draw it as best as I can on this. We've got our x and our y axis. I'm also going to list that the mass of the chair was 25 kilograms, and we're asked to find what mu k is equal to. And then of course the chair is here in the middle. It also said that for this problem we were moving at a constant velocity in this direction here. So what do we know from this? Well, it said that we have an applied force, Fa, of 127 newtons. And since we're moving at a constant velocity, we know that our kinetic friction has to balance that. We also have the weight. This is our force of gravity acting downward. And we have our normal force upward. Okay, so these are the forces that we have. That's our free body diagram. The next step is to sum up all the forces. So we want to add up all the forces, in this case on the x-axis first. In the positive direction I have Fa. In the negative direction I have Fk. And since I'm moving at a constant velocity, the net force is going to be equal to 0. I have two equal signs, but I only need this stuff here. You can see from this that Fa equals Fk. Let's also sum up all the forces on the y-axis. So in the positive direction, I have the normal force. Downward, I have the force of gravity. And again, we know that this is equal to 0 because there's no motion on the y-axis. I have my two equal signs, but I only need one, so I'm going to use these. And you can see here that Fn equals Fg. So what else does Fg equal to? Well, if we go back and think about Newton's second law, which says that F equals ma, we can use this generically for any force. But if I have gravity's force, Fg, then my acceleration is gravity's acceleration. And so then what I can do is a little bit of substitution, right? I can take this here and I can put that in where Fg is equal to. So then I know that Fn must equal mg. Now, because this is a simplified problem where we don't have a huge amount of information, you could actually do this in 3 different steps, right? Step 1 would just be listing that these two are the same, equal to 127 newtons. You could do a quick calculation over here, and you can also get the normal force. And once you have the normal force in kinetic friction, you certainly can use that to get your coefficient of friction. Remember, the other step after summing up the forces was to use the friction equation. So in this case, we want to find what mu k is equal to. Well, mu k equals Fk over Fn. And now we know that Fk equals Fa, and we know that Fn equals mg. So why not do a little bit more substitution? We can take what Fk is equal to, which would be, let me rewrite this for you. This is Fk. We can take what it's equal to here, Fa. We can just throw that in. We can also take what Fn is equal to, and we can put that in over here. If we do that, and we put Fa over mg, now we have that one equation. I could rewrite it as mu k equals Fa over mg. And this would be the equation that solves the problem. You don't have to do it this way. You could do this in 3 steps, or you could do some substitution and do it all in 1 step. If we put the numbers in for this, we have 127 newtons for that applied force. The mass was 25 kilograms. And we've got 9.81 meters per second squared, as always, for gravity's acceleration. Our calculator gives us 0.52, and that will be what our coefficient of kinetic friction is for number 1, right? This was the chair that was sliding across the floor. Okay, so let me clear the board, and then we'll do number 2. So for number 2, again, we're going to draw our free body diagram. Always want to start with that. Here's the X, here's the Y. This is the ground. I'm not sure if I wrote floor on the other one. I probably should have done that. And our object, in this case, it's the child in the sled, goes here. We know that the mass of the child in the sled is 35 kilograms. And again, we're asked to find what mu k is equal to. In this problem, however, we've got our applied force like this. It's above the axis. The applied force is 140 newtons, and it's directed at 35 degrees to the ground. We also know that we have an acceleration in the forward direction as we're pulling this kid across the snow of 1.25 meters per second squared. Now, because we have our force that is not on an axis, just like we've done in the past, we have to resolve that applied force into its components so that we have an x and a y component. So if I drop down a line that's perpendicular to each axis, this here is Fa's x component. This here is Fa's y component. I'm accelerating, so I know my frictional force, I'm just going to write it underneath here, is going to be a little bit less than my applied force. I could have probably drawn it a little bit smaller. We also have gravity pulling us downward, Fg. And we're on a surface, so we still have the normal force pointing upward. So now all we need to do is look at the forces that are on each of these axes, and we'll sum up the forces just like we did in the previous problem. So in the x-axis, in the positive direction, I have Fax minus Fk, that's opposing me, but now I make this equal to Ma because I have an acceleration. I know I have to use a friction equation at some point, so I'm going to take this stuff here and solve it for Fk. So when I rewrite this, so it says Fk equals, I have Fax minus Ma. Now Fax we know is the adjacent side, so I'll use cosine. So Fk equals Fa cosine theta minus Ma. Let's move on to the y direction just for the time being. So in the y direction, what have I got? Well, pointing upward, I have the normal force. Plus, I have the y component of my applied force. Gravity is pulling us downward. And I'm going to make this equal to 0. So even though I have an acceleration for this problem, the acceleration is not vertical. It's on the x-axis, which is why I keep this equal to 0. Because I'm actually at rest on the x-axis. I'm sorry, on the y-axis. So just like before, I just need this stuff here. And I know that the normal force is in the friction equation. So I'm going to take this and solve it for Fn. And when I do that, I have Fg minus Fay. Recall from the other problem that Fg equals mg. And since I used cosine over here, because it's the adjacent side, the y component here, it's really this dotted line. That would be the opposite side. So this would be Fa sine theta. Now for this problem, you certainly could do this in multiple steps, because the next thing that we need to do is we need to use our friction equation, and that would be, let me just give myself a little bit more room here, uk equals Fk over Fn. So we know that we can find what Fk is equal to here, and we also know we can find what Fn is equal to over here. And you can certainly do that in 3 steps. So step 1 would be to find Fk, step 2 would be to find Fn, and then lastly step 3 would be to find what uk is equal to. So that is one option. If you do that and you put all the numbers in, I'm not going to do that for you, you can put them in the calculator, you'll find that this will be equal to 70.9 newtons, and then your normal force will be equal to 263 newtons. And if you put those into this friction equation, we've got our 70.9 newtons, and then we have our 263 newtons, and we get a value for mu of 0.27. So we'll call that option number 1. Option number 2 is, again, we could use our substitution. We know that mu k equals Fk over Fn. Well, what is Fk equal to? All of this stuff. And Fn is equal to all of this stuff. So I could do some substitution, and in place of Fk, I'll write Fa cosine theta minus Ma divided by mg minus Fa sine theta. And if you did that, if you used this bigger equation that solves the problem, you put all the numbers in, provided that you put them in correctly on your calculator, you're still going to get 0.27 from UK. So that's 2 examples of how we use our free body diagrams, summing up the forces and our friction equation to solve some force problems. So give the other ones a try, and the next time we'll do some problems where we have a slope, like a ramp or a ski slope, something like that. I'll see you in class.